Today we're going to talk about number systems and binary numbers. For the math averse, if you can do 1 plus 1 plus 1 and get 3, and you can multiply by 2, you can do all of the math you need for this course. Okay? There is some notation, some mathematic notation that maybe you haven't seen before. I'm going to explain it. It'll be okay. Just don't let the notation scare you. You can do this stuff, okay? Anybody have any questions about that? Okay, we use numbers as abstractions to represent physical quantities. So I have 5 oranges there, and the cave dweller might have used tally marks to represent those 5 oranges. The Romans were somewhat more advanced. We have the Roman numerals there, and you know what? That looks a lot like tally marks, doesn't it? Maybe they weren't as advanced as we thought. Modern numbers come from the Arabic Indic number system, and I got 7 of those, don't I? And I've been saying 5. Oh well, maybe I should look at this screen, which is closer. All right, Arabic Indic number system, which is the one we use currently. But the point of this is that those numbers represent abstractions. There's nothing really concrete about the number itself other than the value. And we use a set of symbols to represent values. So with the Arabic Indic numbers, we use the 0 to represent the empty quantity, the none. And we're going to find out that 0 is critically important in a positional number system. And then 1, 2, 3, 4, 5, 6, 7, 8, 9 to represent those corresponding values or quantities. The cave dweller, and mostly also the Roman, the symbol itself conveyed almost all the information. And I hedge almost there because the Romans were this close to inventing a positional number system. They didn't make it, but they got close. The decimal number system that we use every day is positional. That is, the value of a symbol depends not only on the symbol itself, but where it appears in the number. And that means that 700 is very different from 007 because the 7's in a different place. I have the same symbols, but they're in a different order. Okay, you knew all of this. I think you probably learned it in the 2nd grade, right? What we're going to do is expand on it, and I wanted to be sure that everybody started from the same point. The decimal number system is also called the base 10 system or radix 10 number system. All 3 of those terms mean the same thing. There are 10 symbols, starting with 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you asked your 2nd grade teacher why we use a base 10 number system, your 2nd grade teacher would hold up 10 fingers. That is bogus. That is bogus. Because guess what? With 10 fingers, we have 11 symbols. We have the none symbol as well. And we'd have a base 11 system if that were the right answer. But it makes 2nd graders happy. So I guess that's okay, huh? Every positional number system starts with a ones place on the right. And then we have powers of the base. This is a base 10 system. So the next one is the tens place, which is 10 to the 1st power. And then hundreds place, 10 squared, and thousands, and 10,000s, and 100,000s, and millions. And when I'm doing this with 5th graders, I say, how high can we go? And they say infinity. And then I tell them that we couldn't really do arithmetic on infinities and say we can write numbers that are arbitrarily large as we need. Can't really write infinities, but we can write numbers that are arbitrarily large. So our decimal number system looks like this example. 1,037 is 1 times 1,000 plus 0 times 100, 3 times 10, and 7 times 1. This maybe we got to the 3rd grade with this, right? But we're still doing elementary school numbers. Okay, a couple of mathematical rules. And if this were a math class, we'd prove this stuff. We'd prove theorems that say this really works this way. It's not a math class, so I'm going to tell you that these are rules to remember, and we'll go on from there. If you care to prove either one of these things, go for it, but don't ask me to do it, okay? All right, rule number one, any number to the power 0 is 1. Interestingly, 0 to the power 0 is 1. That rule is completely general. Any number to the power 0 is 1. The second rule is any number to the first power is itself. So 10 to the 0th power is 1, and 10 to the first power is 10. And that's true. It doesn't have to be 10. It can be any number, just like the rules say. And then we can go on up. 10 squared is 100, 10 cubed is 1,000, and so on. And now we can take that 1,037 and write it as a series in powers of 10. So 1 times 10 to the third plus 0 times 10 squared, 3 times 10 to the fourth, and 7 to the first, and 7 times 10 to the power 0. We have exceeded elementary school when we did this, right? Maybe you're a freshman in high school, or maybe you're in middle school. Any number times 0 is 0. So there in the middle, we have 0 times 10 squared. That does not contribute to the value of the number, but it is critically important because it's the placeholder that pushes that 1 over into the thousands place. If we didn't have the 0, we wouldn't be able to have an effective positional number system. Now, some ancient cultures tried positional number systems without that placeholder symbol. They'd use a space instead. Well, it's very difficult to tell a space that moves a digit over to the left from sloppy writing. You really have to have that symbol that says there is nothing there in that particular place in the number. So 0 is our friend. The 0 is the thing that moves the 1 over to the thousands place and lets us be sure we know where the 1 is. With just those digits 0 through 9, I can express any integer however large. So we help the middle schoolers learn the definition of arbitrarily large so that they don't say infinity. But we can represent any integer however large it might be. And I would ask the middle school kids, well, how would you do that? If I name a really big number, could you name one that's bigger? And they say, sure, you just add 1 to whatever you named. The middle school kids are with it, right? The form of an n-digit decimal number, and we're going to start on the right with a sub 0 times 10 to the 0 power. Remember, 1's place always on the right, and any number to the power 0 is 1. And then a sub 1 times 10 to the first power, and a sub 2, a sub 3, a sub 4, and finally over on the left there, a sub n minus 1 times 10 to the n minus 1 power. The n minus 1 comes from starting with 0 on the right. Anybody have any questions about that? That's the first serious mathematical notation that we've seen this morning. All right, we can represent that a little bit more compactly this way. That bendy thing there is the capital Greek letter sigma. Who's in a fraternity or sorority? Not even one. Okay. You can expect the fraternity and sorority kids to recognize the Greek letters. Oddly, I was faculty advisor to a sorority for many years. They kept re-electing me because I let them alone. All right. So that Greek letter sigma, which if you were a fraternity man or sorority woman you would recognize, is the mathematician's symbol for summation. It's the add them up symbol. The number under the sigma, I equals 0, is the starting point of the sum, and the number above, n minus 1, is the ending point. And then for every I from 0 to n minus 1, we're going to add up a sub I times 10 to the I power. Anybody have any questions about that one? That may be something that you haven't seen before, depending. Yes? Okay, look up into the middle of the slide. A sub 0 times 10 to the 0 power on the right of that expression in the middle. And then we go from a sub 0 to a sub 1, 2, 3, 4, 5, and I'm just using I as a counter. I is going to start at 0 because of that I equals 0 below the sigma, and end at n minus 1 because of the n minus 1 above the sigma. And then I just, instead of writing that whole long string of a sub 1, a sub 2, a sub 3, I compact it up and use sigma notation. And remember, if one of you has a question, probably 3 or 4 of you have the same question. So ask. We're going to talk for just a minute about counting and enumerating. They are not quite the same thing. With one decimal digit, I can count from 1 to 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I have to stop because I am out of one decimal digit. But I can enumerate 10 things because I can number things starting with 0. And it is to emphasize that your textbook has a chapter 0. There's nothing wrong with starting with chapter 0. And in fact, it's the way we get the most work out of those 10 decimal digits. So I can count to 9, but I can enumerate 10 things. I can count with n digits, where n is any number. I can count to 10 to the nth power minus 1. So if I have 3 digits, 10 to the third is 1,000. But I can only count up to 999, right? But I can enumerate 10 to the n things because I can number something with a 0. This is going to be important when we start addressing memory and have a memory location 0, or addressing disks and have a disk track 0, block 0. So I want to get it familiar and comfortable now, so when we start using it, I don't get the, huh? What are you talking about? The same thing is true of numbers in other bases. I can count to, in this case, 10 to the n minus 1. I can enumerate 10 to the nth power things. All right. So far, we've only been talking about non-negative integers. I can have a 0, but I can't have a negative number. We, in pencil and paper arithmetic, add a plus sign or a minus sign. The plus sign is there for negative, the minus sign is there for negative numbers. The plus sign is there if we need to be reminded that something is positive. Same stuff as before. I've just stuck an operational sign in front of it. Okay? Nothing new or fancy. Decimal fractions, 0.1, that is 1/10, and it's also 10 to the minus 1 power. 0.01, that's 1/100th, that's 10 to the minus 2 power. So our decimal fractions are negative powers of 10. And we're going to find out that that works in other bases as well. Not all fractions can be represented exactly. The fraction 1/3 cannot be represented exactly with decimal fractions. But I can be as precise as I need to be. If 0.3 is not close enough, I can say 0.33 or 0.333 or a zillion or so threes. Now there is a problem with that, and the problem is that when we do things with computers, we're doing finite precision arithmetic. So I can't have an unlimited number of 3s. I've got a limit, and the limit is the size of my computer word. Okay? Okay, decimal numbers, base 10 numbers, based on power series in powers of 10, the sum of that series. But there is nothing magic about 10. Not even the 10 fingers that we have is magic about 10. Here's the same positive or negative in sigma notation, and I've replaced the 10 with a b for base. So the base just became a variable. And I can plug anything I want to in there. Now that's not quite true, but I can plug any small integer in there without causing a great deal of consternation. Okay? If I have a number in base b, I need b symbols. B symbols to represent the digits, and the power series will be in powers of b. All right, let's look at a base 8 number. I need 8 digits, and I'm going to choose 0, 1, 2, 3, 4, 5, 6, and 7 to have the same values that are already familiar to us. Okay? I could pick any 8 symbols that I wanted, but if I pick the ones that are already familiar, this is a little bit less weird. The power series is powers of 8, and that 624 sub 8 introduces a new little bit of notation. If the base of a number system is not clear from the context, I'm going to indicate it with a subscript. So that subscript 8 says 624 is a base 8 number. It's not 624, the base 10 value. So that, starting from the right, is 4 times 8 to the 0 power. What's 8 to the 0 power? 1. Good. Sing out. Why is it a 1? Louder than that. I'm old and deaf, and I'm sure they can't hear you over there either. Anything to the power of 0 is a 1. Any number to the power of 0 is 1. Okay. Then we have, so that's a 4 times 1. Then we have 2 times 8 to the first power. What's 8 to the first? 8. What's the rule? Anything to the first power is itself. Good. And then we have 8 squared. 8 times 8, that's 64, isn't it? And then we could have an 8 to the third and fourth and fifth, but then I would get lost and my hair would hurt. So we have 4 times 1, I started on the right, plus 2 times 8, plus 6 times 64, and I can add all of those up, and that 624 base 8 is a 404 base 10. See how I did that? Okay, we're done with base 8 now. Some very early computers with very odd numbers of bits in the words used base 8 or octal numbers. We're not going to do that because that's obsolete. But I wanted to show you a base other than 10 and not 2, because we're going to do a bunch of stuff with base 2 in a minute. So that base 8 was just to convince you that I could have any number I wanted to as be the base. Okay. Any number I wanted to has some constraints on it. If I have a base n number system, I change notation. I need n symbols. So base 10, I need 10 symbols. Base 8, I need 8 symbols. How many would I need for a base 6? I promise you I'm going to ask you that on an exam. I promise you. How many symbols would I need for a base 6 number system? 6. All right. See, you can do this stuff. If I said how many and why, what would you say to the why part? A base n number system needs n symbols. Right? So right up there. The digits enumerate values beginning with 0 and going to n minus 1. So our base 10 number system doesn't go to 10. It goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Our base 8 number system goes 0, 1, 2, 3, 4, 5, 6, 7. Okay? So we go from 0 to n minus 1. I've got n symbols, but I go from 0 to n minus 1. Okay, a smaller base means I need fewer symbols. But a larger base means the numbers are more compact. I needed a 624 to get that 400 and something decimal in base 8. So if I have a larger base, I might need fewer digits to represent a value. Now, so far, we have talked only about integer bases, whole numbers for bases, and that's all we're going to do in this class. Yes, it is possible to have number systems with fractional bases. That'll harm you to think about that. It'll make your hair hurt. Mathematicians do that and publish learned papers and win prizes. But we're not going to do it, and after right now, we're not even going to think about it, okay? Whole numbers as bases of number systems. Everything that happens inside computers happens with the binary or base 2 number system. The bi in binary is the same as the bi in bicycle. If I have a base 2 number system, I need how many digits? 2. And I choose 0 and 1, 0 being the placeholder for the no value at all, and 1 being the unit value. I could have used a couple of typographical symbols or something, but it's a whole lot easier if we choose 0 and 1. The power series is in powers of 2, so here is an example of a binary number, 10111, and that subscript 2 says that's a binary number, not 10,111, okay? And if you start reading binary numbers as though they were tens of thousands or hundreds of thousands, you'll confuse yourself. Don't do that, okay? So that is, on the right, 1 times 2 to the power 0, and then plus 1 times 2 to the power 1, plus 1 times 2 squared, plus 0 times 2 cubed, plus 1 times 2 to the 4th power. That's not on the slide, but we're going to do a lot of that before the day is over. Okay, here are some powers of 2. 2 to the 0th power is 1 because any number to the power 0 is 1. 2 to the 1st power is 2. And then 4, 8, 16, 32, 64, 128, 256, 512, 10, 24, 20, 48, 40, 96, how high did I go? 81, 92. Each one of those is twice the value of its predecessor. Although it might be a picky and fiddly task, if you can remember 2 to the 0th power is 1, you can compute the value of any power of 2. Now, I'm going to tell you, I almost never ask college students to memorize things, but I'm going to give you some powers of 2 that will make your life easier if you memorize them. But you don't have to. You can start with 2 to the 0th power is 1, and then each successive one is twice as much. So 1, 2, 4, 8, 16, 32, 64, okay? Each successive power is twice the one before it. At least for small values, you can do that in your head. By the time I get to what's twice 8192, I might actually need a pencil and paper, okay? It's 16,384, but I did not do that computation in my head. I remembered it because I've been teaching this stuff for a quarter of a century. All right, some powers of 2 to memorize. 2 to the 4th is 16. We're going to see hexadecimal numbers on Tuesday. And, well, never mind. We're going to see hexadecimal numbers on Tuesday. 2 to the 8th, 256. 1 byte, 8 bits, 1 octet. can have 256 different values, 0 to 255. 2 to the 10th, 1,024, that's 1K. And 2 to the 20th, 1,048,576, that's 1 meg. And for this course, I do want you to remember 2 to the 10th is 1024. 2 to the 20th, about 1 million is enough, okay? You don't need to remember whatever that is, 1,048,576. 2 to the 20th is about 1 million. 2 to the 30th is about 1 billion, 1 gig, okay? And once again, you don't need to memorize the exact number. Some of you will do that because it's easy to do, but you don't need to. 2 to the 32, 4.2 billion. That's 4 gigs. And at this point, you really do kind of need to remember the 4.2 or maybe even 4.29. 2 to the 32 is the most of anything that you can address, that is, enumerate with a 32-bit word. And it's because we started having large memories and large disks that the idea of a 64-bit computer became necessary. The architecture of a 64-bit computer was another one of those things that'll make your hair hurt. But we ran out of room in 32 bits. Okay, names for powers of 2. We started out using kilo or kilo, mega, and giga. 2 to the 10th is 1,024, and that's pretty close to 1,000 to 1 kilo. But as we get into higher powers of 2, the binary values diverge from the decimal values. The International Electrotechnical Commission, which is one of those standard setting bodies, set up some names for powers of 2. You don't need to memorize these either, but you do need to recognize them, okay? Similar to kilo, mega, and giga, but they contain the syllable BI to remind us that these are binary values. Here's the table. It's also in the textbook. So 1 kibibyte is 1,024 bytes. We get the extra 24 there. A mebibyte is a little over 1 million. A gibibyte is a little over 1 billion. Okay? Now, the bad news is that these values are not used consistently. So I suggest that when you are trying to be precise, that you use the IEC names. But when you are reading other people's material, read it with some skepticism, okay? A 4 terabyte disk does not have 4 times what is tera on there, tebi, does not have 4 times 2 to the 40th bits. It's got 4 and some number of zeros bits. I lost track of how many zeros it needs. It needs 9 zeros. It's got 4 and 9 zeros worth of bits, or bytes. So you have to watch out for that stuff. Okay. Now, on this slide and also in the textbook, I refer to numbering bytes. The IEC standard says it can be anything, so I could have 1 GB word of memory. Nobody does that. We use those prefixes for bytes. Okay, you have seen this when we were looking. Who was the guy, the basketball player with the number 0? That was a Lakers uniform.
Nick Young?
Yep, exactly, Nick Young. I knew somebody would know that. And I didn't know it. It had leaked out of my head. I knew it when I was prepping this stuff, but I didn't know it while I was standing up here. Okay, counting starts with 0. So with 4 bits, I can count from 0 to 15. With 8 bits, I can count from 0 to 255. With 10 bits, I can get up to 1,023. I can enumerate 2 to the n things, but I can only count to 2 to the n minus 1. How do I convert binary to decimal? Well, there's a binary number, and if we look at it, 2 to the 0th power on the right, so I've got 1 times 2 to the 0, 1 times 2 to the 1, 1 times 2 squared, 0 times 2 cubed, and 1 times 2 to the 4th. Remember to start, when you're doing this, with 2 to the 0 equals 1. If you can remember, start with 0, you can do this stuff. Okay, then we write down the decimal values of the powers of 2. 2 to the 0 is 1, 2 to the 1st is 2, 2 times 2 is 4, 2 times 4 is 8, 2 times 8 is 16. Just double the value each space. And then add up the ones for which the bits are 1. I'm going to skip over that 2 cubed because it has a 0 there. Okay? 16 plus 4 plus 2 plus 1 is 23 base 10. Everybody see how I did that? Who has a question about that? I guarantee you're going to have to do some of that. Can I explain it again? Maybe. Let's see if I can. All right. We're going to remember that 2 to the 0th power is 1. We're going to start at 0. I'm going to write down under that rightmost bit a 1. And then I'm going to double. 1, 2, 4, 8, 16, 32, 64, 128, 256. Just double for as many bits as I need. And then I'm going to add up those values where the binary digit is a 1. And you can think about that as the rightmost bit being 1 times 1. The next one is 1 times 2, 1 times 4, 0 times 8. But we don't need to do any multiplication, right? It's either 1 and something times 1 is itself, or 0 and something times 0 is 0. So there's no actual multiplication that happens in there. Did that help?
Yes, so on the quiz or test, we'll get a set of numbers like 1, 0, 1, 1, 1. And then we'll have to get to the 23 base 10.
Yes. You'll get some binary numbers. You might have to go the other way too, and I'll show you how to do that. Other questions? How are we doing for time? All right, how do I convert decimal to binary? I'm going to do repeated division by 2. Okay, I'm going to carry the quotient down, write the remainder on the right, and then do that over and over again. So if I'm going to convert 23 decimal to binary, 23 divided by 2 is 11 with a remainder of 1. You did this in second, maybe not until 3rd grade. I think we were doing fractions by 3rd grade, had division down. All right, so there we are. 23 divided by 2 is 11 with a remainder of 1. 11 divided by 2 is 5 with another remainder of 1. 5 divided by 2 is 2 with a remainder of 1. 2 divided by 2 is 1, and there's no remainder. This is 0. 1 divided by 2 is 0 with a remainder of 1. And the quotient of 0 says the algorithm terminates. When we get a quotient of 0, the algorithm terminates. You read that from the bottom to the top, 1, 0, 1, 1, 1, which is our old friend 23 base 10. So why does this work? The first division by 2 tells us how many 2's there are in the number, right? And the remainder is how many 1's there are, not accounted for by the 2's. This is very cool. The next division tells us how many 4's there are, and the remainder is how many 2's were left over, so that's going to give us the 2's position, and then how many 8's, and so on. Okay. Okay, I said all of that. 2's place, then 4's place, then 8's place, and 16's place, and we're done because the quotient becomes 0. So there is, in the textbook, this example has a bunch of arrows, curved arrows pointing from the remainders to the binary number to remind you that you're going to read from the bottom up. Okay, that the remainder from the first division is the rightmost bit of that binary number. Okay, how high can we count? We've hit this a couple of times already, and here it comes again, because it's an important concept. With 1 bit, I can count from 0 to 1. Actually, I can only count to 1. 2 bits, I can count to 3. 3 bits, I can count to 7. 4 bits, I can get up to 15. 5 bits, I can get to 31. And in general, I can count to 2 to the n minus 1. And this minus 1 is not in the superscript. First you find 2 to the nth power and then subtract 1 from that. Okay, the minus 1 is not in the superscript. Why do we care? Well, 1 byte, also called an octet, to remind us that there are 8 bits in that byte. The highest number I can store in 8 bits is 255. Can't get a bigger number in 8 bits. Because 2 to the 8th power is 256. I've got 256 values, but one of them is 0. So that's the thing that can bite us, is one of those values is 0. Now then the same thing happens with fixed sizes larger than 8. So in 16 bits, I think 2 to the 16th is 65,536. So the biggest number is 65,535. Up the road here at Kennestone Hospital some years ago in the 1980s, there was a radiation therapy machine called the Therac 25. And the guy who was programming the Therac 25 controller, which was a mini computer, did not know this and allowed some values to overflow. If I add 1 to 255 in finite precision arithmetic, I get 0. And it killed some people. Gave them a dose of radiation that was fatal. This is important stuff. Now, the good news is that modern languages make it modern computer languages like Java or Python make it very difficult to make that mistake. But it's not impossible. You can still mess up. And it's kind of useful, I think, to know why it's difficult, why languages make it difficult to do some things. It's to avoid mistakes that might kill somebody. All right. So I can count from 0 to 255 and no higher with 1 octet. With 32 bits, I can get to about 4.29 billion. If I need more than 4.29 billion, I need more bits, or I need another way of storing information in the computer. And that another way is floating point numbers, which we will get to, I hope, on Tuesday. Okay, today we have 64-bit computers. 2 to the 64th is that huge long number on the slide. It's 4 x-bit somethings, and it's about 1.8 times 10 to the 19th, which is about 18 quintillion. A quintillion is 10 to the 18th. So you can get pretty big numbers in 64 bits, but guess what? That's the biggest number you can get in 64 bits, and sometimes we need bigger numbers, and sometimes we need fractions. So we still have to do something even if we have a 64-bit computer. So we've spent almost 50 minutes, I think, 46 minutes talking about binary numbers, and an entirely reasonable question is, why would you do something like that? We have a perfectly reasonable decimal number system that everybody understands how it works. Why would we build computers that require binary numbers? And the answer is reliability. I guarantee you that this is a test question too. I once tried an experiment that Dr. Harbert, now retired as well, suggested. I gave out copies of the test before test day. People still flunked. The ones of you who are going to make A's are going to make A's no matter what I do. And the ones of you who are not are probably not, no matter what I do. All right, so reliability. Let's think about making a decimal computer. I need to represent quantities with electric signals, right? So I might say I'm going to let a signal of 0 volts represent the number 0, 1 volt represent the number 1, 7 volts represent the number 7, and so on, right? And that starts out seeming very reasonable. But remember, we're representing digits. I'm not representing continuous quantities. I'm representing either a 0 or a 1 or a 2 or a 3. Electronic components are not perfect when they come out of the factory, and we're lucky if we get within plus or minus 10% of the value of the nominal value, the thing engineers call nominal. And components get worse with age. Who has an old music player? Does it sound as good as it did when you bought it? No. No. The properties of electronic components degrade with age, unfortunately for all of us. Okay, so in this hypothetical decimal computer, if I read a signal of 7.2 volts, I'm probably going to call that a 7, right? It's not exactly 7.0, but I'm probably going to call it a 7. If I get 7.8 volts, I'm probably going to call that an 8. What do I do with 7.5? I have one of those undecidable problems. And in this case of a 10% error, I have an undetectable mistake. On the other hand, it is really, really easy to build electronic devices that can distinguish between on and off. When I'm telling this to the middle school kids, I ask them about a music player and I say, listening to the music, can you tell whether the volume is set at 7 or 8? And they pretty readily agree that no, they can't tell reliably. Can you tell whether it's on or off? Oh yeah, I can do that. I can do that. So if we look at a chart, if I need 10 different values from 0 to 9, a 10% error, either plus or minus, gets me a wrong answer. If I only need 0 and 1, I can tolerate a 49% error. I can tolerate really big errors and still get the right answers. We would love to get the right answers out of our computers. No, you don't need to reproduce this. If I say why binary numbers, reliability is the right answer. A one-word answer is good enough. I'm going to give you a several-word answer in just a minute. The first electronic digital computer that we knew about was ENIAC, and it was a decimal computer. And you know how they made that work? 10 vacuum tubes for each digit. 9 of them turned off and 1 of them turned on. Because the engineers in the 1940s knew that stuff that I just told you. They said we can't do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 volts and be reliable. But we can do on or off and be reliable. So they built this thing called a ring counter with 10 vacuum tubes, and turning one off turned the next one on. So like the old mechanical odometers. Is anybody in here besides me old enough to know what that looks like? No. Okay, wheels that were labeled 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 on the edge. And when the rightmost wheel went from 9 back to 0, it had a little peg on it that turned the next one notch. This works the same way. Here's a picture of one. That is 1 decimal digit. The two women who are holding the ring counter are the widows of a couple of the inventors of ENIAC. So they have a reason to be there. But that's 1 decimal digit. John von Neumann said, you know what? If you take those 10 active devices, and there's a bunch of supporting circuitry on there, instead of 0 to 9, you can go from 0 to 1023 with a binary number. And the other engineers said the equivalent of son of a gun. And ever since that day, fairy tales work that way, right? Ever since that day, the internal representation in computers has been binary numbers. Now, the son of a gun thing, if you take the 10 vacuum tubes that are the active components of the ring counter, there's way more than 10 on that device, you can go 0 through 9, or if you use them for binary numbers, you can go from 0 to 1023. So the other part of why binary is that using binary numbers increases the expressive power of binary devices. I can use 10 vacuum tubes to go 0 through 9, or I can use 10 vacuum tubes to go 0 to 1023. Reliability is at the base there, but we also improve the expressive power of each device. So who has questions about that? Well, let's look at binary addition for a minute. I'm going to start on the left of this thing. 0 plus 0 is 0. No problem with that, huh? 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 2. But there's no way to represent a 2 in a single binary digit. So I have a 0 in the 1's place and 1 in the 2's place. And 1 plus 1 is 2, just like we expect. 1 plus 1 plus 1, that's 3. 1 in the 2's place and a 1 in the 1's place. Okay? Want to hear that again? It's on YouTube. Professor Brown and Megan. Megan is a niece, and Megan finished her PhD a few years ago, so she's Dr. Megan now. But at any rate, I'll put the slides up, and you can, if you want to hear that again, watch it on YouTube. Here's a binary addition example with the carries already there. Starting on the right, 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 0 with 1 to carry. Now I have 1 plus 1 plus 0. 1 plus 1 is 0 with 1 to carry. 1 plus 0 plus 1, that's another 0 with 1 to carry. 1 plus 1, and I don't have anything below that, 0 with 1 to carry. 1 plus 1, 0 with 1 to carry, and then we bring that carried 1 down. Now I'm using the word carry because I'm an old guy. Your elementary school teacher may have called that regrouping. Who has heard regrouping instead of carry? All right, everybody's still cool with carry. Okay, I have trouble with the middle school kids with that one because they've never heard of carrying numbers. All right, let's look at binary multiplication. This is cool because 1 times something or 0 times something. 1 times something is just the something, right? And 0 times something is 0. No actual multiplication has to take place. We're going to do multiplication just like we would do decimal multiplication, form partial products and add them up. But look at the multiplier, the 1, 0, 1. 1 times 1101, that's the multiplicand, is just 1101. Okay? 1 times 1101 is 1101. Not tough at all. So that's where the thing labeled ones place comes from. 0 times 1101 is 0. And the 0 is shifted one place to the left. And now we have a 1 times 1101. That's another 1101, and it's shifted one more place to the left. This is exactly what you do when you are multiplying decimal numbers by hand, except we don't have to do any actual multiplication. It's either times 0 or times 1. Then you add up the three partial products, and you get the final product. No, I'm not going to ask you to do that on an exam, but I want you to believe that it works. Division also works. We're not going to even talk about that. Okay? If you look up binary division algorithms with Google, you find division by repeated subtraction, which is a hideously inefficient way to do it. It turns out, remember that you can divide a decimal number by 10 by shifting it right one place. 100 divided by 10 is 10. You can divide a binary number by 2 by shifting it right one place. And so if you can get the factors of 2 of the multiplier, you can do some shifting instead of a bunch of repeated subtraction. And no, we're not going to go into the details of that. In fact, I don't think they even go into the details of that in the computer science architecture course. Okay. All right, so I got ahead of myself. Partial product is either a copy of the multiplicand or it is a 0. No actual multiplication takes place. Finite precision arithmetic, and we've talked about this, I think. Okay, precision is the number of significant digits in a number. If I'm doing computation with pencil and paper and I need more space, I just write down a bigger number, huh? In computers, we can't do that. We have fixed word sizes. 32-bit computers kind of in the recent history, 64-bit computers now. Further back in history, we had 16-bit and 8-bit computers, but always a fixed size, and that's the important thing. We don't get to just add more bits if we need more bits, always a fixed size. And so that business of fixed size is called finite precision, and computer hardware works with finite precision numbers. Finite precision arithmetic is arithmetic on numbers with a fixed number of digits. That is, the precision is fixed. If we forget that, this is why it's important, we can get wrong answers dealing with big numbers, very small numbers, or with complex numerical problems. And there is an example in the textbook about the commutative and associative laws not applying when we're doing finite precision arithmetic. So everybody's reading the textbook, right? It took me a solid year to write that sucker. You better read it. Okay, one of the biggest problems with finite precision arithmetic is this problem called overflow. Overflow occurs when numbers become too big to fit in the space available. So if I have, let's see, I think the odometer in my car is good for 99,999. Now I drove not the current car, but two cars before it for 30 years and 1/3 of a million miles. Watch that odometer turn over twice. But the odometer, when I sold the car, looked like I had driven 30,000 miles. And I had really driven 1/3 of a million miles. That's overflow. You get a wrong answer when overflow occurs. Overflow is the condition that the result is too big to fit in the space available. So, yes.
Kind of to like the whole Y2K problem?
The question was this behind the whole Y2K problem? And the answer was yes. People had, for many years, stored the year part of the date as 2 digits. And all of a sudden, and you could still do that, there was nothing wrong with storing 00 for the year 2000, then 01, and we'd be at 23 now. The problem was comparing dates in the 1900s with dates in the 2000s. Now you can't tell whether 00 is 1900 or 2000. So yes, it was overflow. And I think I told you when we were talking about history that very briefly on January 1st of 2000, the Naval Observatory reported the date as January 1st, 19100. Oops. Well, it took 99, add 1 to it, and there's the date. And they had just plugged a 19 in front of it. So yes, the so-called Y2K problem, which was nowhere near as big a problem as everybody thought it was going to be. The problem came in comparing dates. And so I was working at the hospital, what was then DeKalb General Hospital. We had a 100-year-old baby, and that was the biggest problem we had. And of course, we fixed it instantly. All right, overflow is the condition that the result of an arithmetic operation is too big to fit in the space available. Can I explain the overflow thing one more time? And I'm repeating the question for the recording. Although we did eventually get almost everybody, we're still missing some. If I have, let's say I have 3 digits of fixed precision, decimal numbers. I can add 700 and 100 and get 800. What happens if I add 700 and 300? Doesn't fit in 3 digits anymore. And the 3-digit part's going to be, it's 1,000 when I add 700 and 300. And the 3-digit part's going to be 0. And the 1,000 part is gone because it didn't fit. So we have a wrong answer, and it's way, way wrong. So to give you the definition, overflow is the condition that an arithmetic operation produces a result too large to fit in the available space. I wonder if I can say that twice. An arithmetic operation produces a result too large to fit in the available space. What else? Questions are good. No takers. Okay, thank you very much, ladies and gentlemen. Have a nice weekend. Don't freeze, and I'll see you on Tuesday.